So now I introduce Miro Haller, who's giving us an attack on Radius.
Thank you very much for the introduction. This talk is joint work with Sharon Goldberg, Nadia Henninger, Mike Milano, Dan Shumov, Mark Stevens, and Adam Suhl. And in this talk, we're indeed going back to the time where everyone used MD5. So this talk is going to break Radius. So let's start with what Radius is. There we go. Okay, so you might have never heard of Radius, but the infrastructure that you're depending on most likely is using Radius. Radius is often hidden from the end user, but it's a de facto standard for enterprise network authentication. And as such, it's basically supported by every piece of networking gear that was produced in the last 25 years. So for example, Radius is used to authenticate access to internet backbone routers. Almost all non-cable ISPs are using Radius internally. Radius is also used to authenticate access to internet control systems and power grid controllers. It's also one of the supported ways of integrating with identity providers such as Okta and Duo, and to support multi-factor authentication. Radius is also used inside 802.1x and therefore used for authenticating access to enterprise Wi-Fi or eduroam. Here is one slide summary of our work. Let's start with how Radius is used to connect the user to enterprise network. So let's consider a user that wants to authenticate to a router to connect to Wi-Fi. In that case, the user sends their username and password to the router. But in most enterprise deployments, the router doesn't actually store all of the user credentials. Instead, there is a centralized authentication database. And so the router, acting as the Radius client, asks the Radius server whether or not it should grant this user access. And it does this by sending an access request Radius message to the server. The server will then consider the authentication database and decide whether or not to give the user access by sending back a message that's called an access accept or access reject Radius message. And based on that, the router then grants the user access or not. So this is really hard to believe, but Radius is actually using a custom MD5-based MAC to authenticate packets, and it's also sending most of its packets over UDP, in many cases even over the public internet. The attack that I'm presenting here is called Blast Radius. It's a protocol vulnerability that allows a machine in the middle to change an access accept to an access reject, the other way around, a reject to an accept. The impact of this is that an adversary using this attack can authenticate as any user. So for example, if Radius is used to authenticate access to internet backbone routers, then this allows the adversary to authenticate as administrator. Our work also helps to accelerate the ongoing efforts to deprecate Radius over UDP in favor of Radius over TLS. We disclosed this attack to over 90 companies, including all vendors, all big vendors of network equipment, such as Cisco and Microsoft. I hope I piqued your interest in Blast Radius, and in the remainder of this talk, I'm going to talk about how this attack works on a technical level, as well as how mitigations are going. So let's start with a few aspects of the Radius protocol that are important for our attack. In Radius, all packets start with a 4-byte header that specifies the packet length and the packet type. The access request then has a 16-byte nonce that ensures the freshness of responses. And finally, it also has attributes, including the username and a scrambled password. This scrambling, by the way, is also extremely sketchy. It uses MD5 as a block cipher with a custom cipher feedback mode in cipher feedback mode. But that's actually not the part that we're breaking. So back to the packet formats, the access accept has a response authenticator, which prevents the forgery of responses. It also has attributes. For example, it defines what kind of privileges the Radius client should give the user that is authenticated. The reject has a similar structure. but usually less attributes. So as you can probably guess, the target of our attack is this response authenticator. So let's see how this is constructed. As the name suggests, the response authenticator should prevent an adversary from forging packets that are sent, for example, by the Radius server. And for this, it's using a custom MD5-based construction, which is the following. To compute a response authenticator of a packet like this, we take the MD5 hash over the response header and attributes that are copied from the response, the request nonce that's copied from the access request to which this is a response to, as well as a fixed pre-configured shared secret. This shared secret is set up at the time when the Radius infrastructure is set up, and it's hard-coded on both the Radius client and the Radius server. And this is exactly what should make it hard for an adversary to forge packets, because the adversary doesn't know the shared secret. Now, at this point, probably all of you are thinking, was MD5 maybe broken like 20 years ago? And you're right. That is exactly the case, and that was the start for our research. So let's see how the blast radius attack works. The goal of our attack is to forge an access accept without actually knowing this shared secret. And in order to be able to do that, we need to get around this response authenticator. And that's exactly where we're going to use the MD5 collisions. So basically, roughly speaking, our goal is to create an MD5 collision between a forged access accept and the predicted access reject, such that both of them produce the exact same response authenticator. So on a high level, this works as follows. The adversary logs into an account with some random bogus password, which then causes the Radius client to send an access request to the Radius server. But this request is intercepted by the machine in the middle, which is then using the information in the request to predict what access reject the server will send back. And it's then running a collision algorithm to compute a matching access accept that has the same response authenticator. But at this point, the adversary doesn't know what this response authenticator is. So to learn that, it modifies the request to make sure that the server sends back the access reject that is predicted. And once it gets a reject, it can just copy over the response authenticator to the accept. And this will trick the Radius client into giving the adversary access to this user, although the adversary never actually knew the correct password. Now, I've been very hand-wavy about how this collision works. So let's look at this in more detail, starting with a quick refresher on the MD5 collisions. The first weaknesses were discovered in 1993. And then in 2004, the first full MD5 collision was discovered. So this is a collision between two unstructured strings of bytes that we like to call gibberish. And the adversary can compute these in seconds on a laptop, but they don't actually have a lot of control over the collision. And so that means it's pretty hard to use these type of collisions in real-world attacks. And as we all know, to get broken cryptography out of applications, we need the clicker stopped working. We need exploitable attacks that break real-world applications. There we go. There you have your meme. All right. So the next stronger attack is called an identical prefix collision, which basically gives the adversary, given a static prefix, can compute two gibberish strings G1 and G2, such that the MD5 hash of the prefix appended with the gibberish strings collides. This was famously used for the shattered attack to create two PDFs that have the same SHA-1 hash. And while this was a very expensive computation for SHA-1, this is actually not so expensive for MD5, so you can do this in seconds to minutes. The strongest type of attack is called the chosen prefix collision attack, where the adversary gets to specify two different prefixes, P1 and P2, and then can compute with the attack gibberish strings G1 and G2, such that the MD5 hash of P1 concatenated with G1 is the same as the hash of as the MD5 hash of P2 G2. And this was used in 2009 to create a rogue TLS certificate on a farm of 215 PS3 machines, and it still took over 28 hours, or it took 28 hours. So this is clearly more expensive. An interesting fact is that once we have a collision, we can also append an identical suffix to both of the MD5 inputs. And due to the Merkle-Damgard structure of MD5, this still creates a collision, given that you have the right padding. So now that we've seen that you can compute, although you can compute MD5, generic MD5 collisions within seconds, what we need for blast radius is actually the more expensive chosen prefix collision attacks. And actually, we need to compute them in less than 5 minutes, and while satisfying additional constraints, but more on this later. Let's first discuss how we use those collisions to refine our understanding of the attack. So recall that the goal is to use these MD5 collisions to forge an access accept that has the same responsive indicator as a predicted access reject. So to do this, the adversary sets the header, nonce, and attributes of both the accept and the reject as the prefixes, then runs the MD5 chosen prefix collision attack to compute gibberish strings for the accept and the reject. And at this point, the prefixes and the gibberish both collide. But as we've seen before, this value still collides if you append the same suffix to both of them, which is very convenient for our attacker because the adversary actually doesn't know this shared secret that's appended, but it is the same in both cases. This is also, by the way, where the discussion of the IETF working group was focusing on protecting against length extension attacks, which they protect against with this secret suffix, but that doesn't help them against collision attacks. And so that's one of the sources for this, why this attack happened. So at this point, you in the audience might wonder if it can really be that easy to break radius with MD5 collisions. And on that, even the IETF working group, they were aware that MD5 was broken, of course, but they thought it's a testament to the design of radius that there have been back then no attacks on the radius authenticator signature, which is actually a MAC. And indeed, there are quite a few challenges to pull this attack off in the protocol, and I'm going to discuss 3 of them. The first challenge is that we must convince the server to include the reject gibberish in its response authenticator computation. And that seems a little bit impossible at first, because why would the server include some arbitrary bytes that the adversary picks in its computation? But lucky for the adversary, the standard defines something called the proxy state attribute, which is truly perfect for our attack. And this attribute is mandated by the RFC that this attribute must be returned without any modifications in the response. And so what the adversary can do is it can put the reject gibberish in a proxy state attribute in the access request, and then this attribute will be copied over to the reject. And so it will be included in the response authenticator computation. But there we run into the next problem that it's actually too expensive and too slow to compute a reject gibberish that's short enough to fit into a single proxy state attribute. And so to resolve that, we had to improve on existing chosen prefix collision attacks and to allow us to fix a 4-byte proxy state header in the middle of the gibberish string. And that allows us to spread the gibberish across multiple proxy state attributes. The last challenge that I'll talk about is that, unfortunately for the adversary, the response authenticator also includes a request nonce that's picked at random for the request. And so it can't actually pre-compute the MD5 collisions. It needs to first observe the nonce, and then it can use the prefixes. And so that adds a time constraint, because the adversary needs to compute this collision before the radius client times out, which in practice is at most 5 minutes, usually less. And so we had to optimize our computation. At the first, when we implemented this, it took multiple days to run this, and we got it down to below 5 minutes. You can obviously ask, can we go faster? Can we go below 1 minute? The answer to that is yes, we can definitely do that. That's just all we got out of our 10-year-old hardware, banging our heads against it for a while, but you can definitely go faster. Let's move on to impact and mitigations. Our attack breaks the PubChop and MSChop authentication modes of Radius. It doesn't affect the EAP authentication mode. And this is because that authentication mode requires an additional attribute that's an HMAC MD5. And this attribute is not vulnerable to MD5 collisions. And an interesting fact is also that Radius, the EAP TLS authentication mode, which nests the broken, which nests EAP TLS inside the insecure radius, is also saved by this HMAC-MD5 attribute and not actually the fact that it's using TLS. And so this is not to be confused with the correct way of doing this, which is nesting radius inside a secure TLS channel. That's called radius over TLS. Our attack also requires machine-in-the-middle network access. And so that means if your deployment sends radius traffic over UDP over the public internet, then you're definitely vulnerable. Now, you might ask, or you might think that no one is doing this, but it turns out that surprisingly many organizations are doing this, including most non-cable ISPs, as well as major cloud providers. Or to put it into the words of the free radius maintainer, Alan DeCock, lots and lots and lots of people are sending radius over UDP traffic over the public internet. Now, if your deployment sends radius traffic over a separate VLAN or an IPsec tunnel, then the adversary would first need to compromise that network. But once they have compromised it, they could use blast radius to spread onto all devices that use radius for authentication over that network. We discussed this attack to over 90 vendors, and in the long term, we suggest to wrap radius traffic inside TLS so that we can rely on TLS for integrity and confidentiality. And there is an ongoing effort in IETF to standardize radius over TLS and also afterwards deprecate radius over UDP. However, in practice, this is hard to deploy. One of the reasons is that radius is used very broadly. For example, one of the use cases is even to for remote access to windmills in power plant controllers. And so some of these implementations are really hard to upgrade, which makes backwards compatibility a major constraint. And so on the short term, in discussions with vendors, we suggest to use the message authenticator attribute that I discussed before, because that's already supported in the standard. However, this only works if you use this attribute to authenticate all requests and responses. So let's see how this is going. The good news is that all of the radius server vendors already had patches available at the time when we went public, and by now most of the equipment vendors also upgraded their systems. However, there is some trouble, some inconsistent interpretations of where to put the message authenticator. So Juniper devices require it to be the first attribute, and Cisco devices put it at a random place in the packet. So if you upgrade both of your Juniper and Cisco devices in your network, you might find that authentication is no longer working. The correct way to do this would be to put the message authenticator as the first attribute when you send packets, but to mandate that it's present, to only mandate that it's present when you receive packets. Why is this so complicated? Well, it turns out that there's an extension to our attack that applies to partial mitigations. Basically, you can hide a message authenticator by extending our attack such that the accept gibberish ends in a proxy state header, in which case the client will parse the message authenticator as a proxy state and never actually verify it. There's more information about our attack on our website, and I'm happy to take questions now or on the hallway later. Thank you.
So there's time for one quick question.
I assume that in most cases, the accept or reject answer is obtained within less than a second. Is there any reason why you allow the system to wait 5 minutes before getting the answer? It would be very easy to put a much more reasonable upper bound, which will not stop any the actual use of the protocol.
Yes, that's a very good question. In practice, most of the applications allow an upper bound until 5 minutes, but the ones that are usually used are between 15 seconds and a minute. The reason why you sometimes want to have a minute is if you integrate it with multi-factor authentication, then you might require the user to go to their phone and click some second factor. And if you set it too low timeouts, then you break the authentication functionality for that. But yes, usually it's used for 1 minute or so, but 5 minutes is how much time we wanted to spend on optimizing our code. You could definitely get to 1 minute.
In relation to that, was the speed up from 28 hours to 5 minutes just modern hardware, or is there new cryptanalysis?
A lot of, we did a bunch of trade-offs that are different from the previous Trojan prefix collision attacks. Definitely all of this is in the paper, but the short summary is that we traded off more computation power by spreading the attack across multiple machines rather than one, and lower success probability for shorter latency, so that our attack succeeds less but is faster and requires more compute but is faster. We also outsource or did more pre-computations and so forth. Yeah, I think the most algorithmic or cryptanalytic improvements are, for example, the inclusion of fixed bytes inside the gibberish, which is a capability that wasn't present before.
Thanks.
So thank you, Miro. Join me in thanking him again.